Hello, friends. Welcome back to the channel. This is Ahili Bhattacharya, and today we are going to study moments in statistics. See, we are diving into a topic that sounds a bit intimidating, but is absolutely fundamental to understanding data. Alright, now you might already know about the mean and variance, but did you know they are just the first two members of a much bigger family? Moments are that family, and they are the secret tools that tell us everything about the shape of our data, where its center is, how spread out it is, how lopsided it is, and even how sharp or flat its peak is. Stick with me because by the end of this video, you will not only understand what moments are, you will see how they all fit together to paint a complete picture of your dataset. Let's get started. First things first, what exactly is a moment? In physics, we already learned a moment refers to a force causing rotation around a point. In statistics, the idea is surprisingly similar. Think of it as a way to measure how data points rotate or balance around a specific value. The general definition is this: the rth order moment about a point A. See, for raw data. What is the formula? Mu r dash is equal to 1 by n into summation xi minus a whole to the power r. Let me write it down. Mu r dash is equal to 1 by n into summation xi minus a whole to the power r. Okay. For frequency distribution, the formula is mu r dash is equal to 1 by n into summation fi into x minus a whole to the power r, where here n is equal to summation fi and I running from 1 to n. Here I running from 1 to r. Okay. Now let's break this down because it's the heart of everything. First, mu. Mu is the symbol for a moment. The dash in mu r means it's a general moment, not a central one yet. Okay? It's a general moment. Next, R is the order. R is the order. It's a like we talk like this, right? Is it the first moment or R is equal to 1, second one, R is equal to 2, etc. This is the power you raise everything to. All right? Now, next, A. A is the point about which we are calculating this moment. This is the most important part that defines the type of the moment. Okay? Next, here. Xi minus a is the deviation of each data point from our chosen point A. Okay, this is the deviation. Next, we sum all these deviations raised to the power r, and then average them. Okay, so in simple terms, a moment is the average of the deviations from a point raised to a power. Now see, there are like two special types of moments. With the value of A we choose is what gives moments their special names and superpowers. As I said, there are two critical choices. First, raw moments, the origin story. Here, the first is when we set A is equal to 0. So our general moment becomes a raw moment. Okay. The formula simplifies beautifully, saying mu r dash is equal to 1 by n into summation xi to the power r, I running from 1 to n. Okay, why is this useful? Let's look at the very first raw moment, mu1 dash. Here, mu1 dash is equal to 1 by n into summation, oh I'm sorry, I wrote f, into summation xi to the power 1, which is equal to 1 by n into summation xi. Does that look familiar? That's just a mean, right? Mu1 dash is equal to x bar. So the first raw moment is the arithmetic mean. It's the simplest measure of where the data is centered relative to the origin 0. Now coming to the next one. But what if we don't care about the origin? What if we want to understand the data relative to its own center? For that, we set A is equal to x bar, the mean of the data. This gives the most important type central moments. You see, we denote them without the dash, mu r only, mu r. What is the formula? Mu r is equal to 1 by n summation xi minus x bar whole to the power r. These moments measure everything around the mean. Let's see the first few, which you already know and love. Alright? First, central moment, mu1. See, mu1 is equal to 1 by n into summation xi minus x bar. Okay, let's calculate that. We get summation xi minus x bar is equal to summation xi. For this part, I'm calculating. Okay, summation xi minus summation x bar, which is equal to summation xi minus n into x bar. And since x bar is equal to summation xi by n, we get summation xi minus n into summation xi by n gets cancelled. So mu1 is equal to 0. Always, the sum of deviations from the mean is always 0. It's a great sanity check. Okay. Now for second central moment, mu2. Mu2. Mu2 is equal to 1 by n into summation xi minus x bar whole square. That's the average of squared deviations from the mean. That is exactly the variance. Alright, this is huge. Okay, so far we have learned raw moment 1 mu1 dash is equal to mean, central moment 1 mu1 is equal to 0, central moment 2 mu2 is equal to variance. But the magic doesn't stop there. This is where the shape of the distribution really comes into focus. See, now let's go beyond variance and meet the third and fourth central moments. These are the stars of the show when it comes to describing shape. See, the third central moment is this mu3. Let me write mu3 is equal to 1 by n into summation xi minus x bar whole cube. Why cube the deviations? Squaring as in variance kills the sign. Negative deviations becomes positive. Cubing brings the sign back. This allows mu3 to measure the direction of the tail. See, first, if mu3 is greater than 0, the positive deviations dominate, meaning there is a longer tail on the right. We call this positively skewed. Number 2, if mu3 is less than 0, the negative deviations dominate, meaning a longer tail on the left. This is negatively skewed. Number 3, if mu3 is equal to 0, the tails are balanced. The distribution is symmetric. Okay, but there's a problem. Mu3 has units like centimeter cube if our data is in centimeter. So to make it a pure unitless number for comparison, we standardize it. We divide it by the standard deviation cubed. This gives us the beta and gamma coefficients for skewness. Here as you can see, beta 1 beta 1 is equal to mu 3 whole square by mu 2 whole cube, and gamma 1 is equal to root beta 1, which is equal to mu 3 by mu 2 to the power 3 by 2. Okay, now we have a key note here. Since beta 1 is a square term, it's always positive. But see, it's a square term, so it's always positive. But gamma 1 here keeps the sign of mu 3. So we use gamma 1 to tell the directions. Okay. First, gamma 1 is equal to 0, then it will be symmetric. And gamma 1, if it is positive or greater than 0, it will be positively skewed. And if it is lesser than 0, then it will be negatively skewed. Now coming here for the fourth central moment. So let me write it here only. Mu 4 is equal to 1 by n into summation xi minus x bar whole to the power 4. Raising to the fourth power heavily emphasizes extreme values in the tails. Mu 4 measures the tailedness or peakedness of a distribution compared to a normal distribution. Again, we standardize it to create a unitless measure, giving us the beta and gamma coefficients for kurtosis. Okay? See, you can see the formulas here. Beta 2 is equal to mu 4 by mu 2 whole square, and gamma 2 is equal to beta 2 minus 3. Now You can think like why subtract 3? Because a perfectly normal distribution, the bell curve, has a beta 2 value of exactly 3. So we use this gamma 2 to measure kurtosis relative to the normal distribution. This leads to three classifications. See, the three curves: leptokurtic, tall and skinny; mesokurtic, normal; platykurtic, short and flat. I have done the graph here. See, leptokurtic, which is, you can see, as I said, tall and skinny; and mesokurtic, which is, this is normal; and platykurtic, which is short and flat. Now, coming here again, see the first point. If gamma 2 is equal to 0, that is beta 2 is equal to 3, the distribution is mesokurtic. Okay? It has medium tails and a medium peak, just like a normal distribution. And point number 2, I'm sorry. Yeah. Point number 2, which is gamma 2 is positive or greater than 0, that is beta 2 is greater than 3, the distribution is leptokurtic. It has a sharp peak and fat tails. This means there's a higher probability of extreme values. Think of data like stock market returns, okay? And point number 3, if gamma 2 is less than 0, that is beta 2 is less than 3, the distribution is platycardic. It has a flat peak and thin tails. This means fewer extreme values. Like think of data like height of adults, which is very clustered. Okay. Now let's do a quick recap of our moment family portrait. First, general moment, mu r dash, the foundation, an average of deviations from any point A. Okay. Point number 2, raw moment. Mu r dash with A is equal to 0 tells us about the data relative to the origin. The first raw moment is the mean. Okay. Point number 3, central moment mu r with A is equal to x bar tells us about the data relative to its own center. Mu 1 is always 0. Mu 2 is the variance. Mu 3 and gamma 1 tells us about the skewness. Alright. And mu 4 and gamma 2 tells us about the kurtosis, tailness and peakness. So from just these few moments, you can get a complete quantitative description of your data's central tendency, dispersion, symmetry, and shape. And that's the power of moments. They are the building blocks for understanding data shape. If you find this video helpful, please give it a thumbs up and share it with a friend who might benefit. So, what statistical topic should we explore next? Let me know in the comments below. And do not forget to subscribe and hit the notification bell so you don't miss our next deep dive. Thanks for watching and see you in the next one. Okay? I'll upload the notes here in the description box. Bye.